In the previous video, I talked about the register file for my Homebrew CPU SPAM-1. I mentioned that it was a triple port device, and I put this schematic up on the screen. And this is a triple port device created from dual port components. So for instance, the 74670 register file chip has got an input and an output, so dual ports. I also mentioned that you could construct a device like this, of course, from dual port devices, and I gave an example of what that would look like, and it was this. But for the sort of function I'm after, this isn't the simplest device that would do the job. It was actually more like this one. And the difference is that when I'm using a device like the 74574, it's got its own output enabled pin. Unlike, say, for instance, the 74273 over here, this latch doesn't have an output enable, so we put a layer of transceivers in front of it to multiplex the output onto the two buses A and B. But where you've got a register file, or register chip rather, that's got its own output enable, it's a tri-state device, then we don't need that extra layer. But what we can do is we can just duplicate the registers. So we can have a bank of registers that relate to channel A and another bank of registers that relate to channel B. And of course, you've got various decoding logic that's in common between the two approaches. But this approach avoids the need for a separate set of registers behind a set of transceiver chips, which is what we've got over here. But to talk about triple port devices, it's actually better to start with something simple. So that's the sort of device that I talked about in my earlier video. We've got a register, and then we've got a couple of buffers that take it out onto the two buses. Most of the time, however, this approach is simpler, just two registers with an output enable, assuming they've got tri-state outputs, that is, and some examples of chips that like that are illustrated here at the bottom. But the reason why this arrangement here came to mind was because that's what I've actually used in my memory address register. And the reason I've done that is because I want to put some LEDs on the output of the register chip. And because that chip is therefore going to have its outputs enabled the entire time, I can't disconnect that to the bus. So I've put a couple of bus drivers in between. Those are the 74245 chips. But if you're starting with something like this, two registers, and you want to build it up to a register file, then you're going to get from something like this to something like that pretty quickly. And whilst I don't exactly have a register file like this, I do have other aspects of my CPU that are somewhat similar. And so I thought I'd just show you a pattern that's actually worked for me. And the approach I've gone for is to use 74138 decoders to provide the control signals to select which of the chips are going to have access to the bus. So I've got 74138 controlling the output enable of the A devices, and other 74138 controlling the output enable of the B devices. So 2 bits in, and then 4 individual control lines out, active low. But when it comes to controlling the latch enable or the clock pulse for the registers to control which register is going to get written to during the write phase, there's actually a hazard. And the hazard is that when the write address changes, the outputs don't jump straight to the expected value. They may jump around a little bit. It may actually go to a different value, or they may go to multiple values, just as a glitch before they settle down into what the expected value would be given the given write address. Now, if you're deriving a clock pulse or a latch enable off the back of that, then you might accidentally enable one of these chips or send a clock signal into one of these chips when you didn't expect to. So it's important to avoid that. So what I've done to avoid getting glitches on the clock pulses into these registers or the latch enable is I've taken advantage of the enable pins of the 74138. It's got active high and active low inputs for enable, so you choose which one you want to use. Now, when the 74138 isn't enabled, its outputs are high, and they stay high regardless of any changes that might be occurring on the write address or logic that's settling within the device itself. So during the phase of the clock where the lines might be settling, I keep the chip disabled. And then when the clock flips to the alternate phase, it enables the chip, and the output lines jump directly to the values that they should have, which could either result in a clock pulse or a latch enable, whatever I need. And that avoids a situation where I get this glitching on the outputs. And I've said down the bottom here that unless a device declares itself as being glitch-free, then you should assume that it's going to glitch during transitions. And most of the time I actually try to design around it, so I try and make the circuit so it's not going to be sensitive to glitches. And usually it'll be some kind of trick like this where I disable something so that it doesn't see the glitches. So I hope that was useful. A couple of patterns there for register files and some hazards to be avoided. Take care.